Do I have to announce when I start? Okay.
Yes.
Yes, okay. So, are there any questions? Okay, so maybe I will start now. So we're talking about, we had started to talk about normal subgroups. So the subgroup H of the group G is called the normal subgroup. If we have the following, so if for all G in P and all H in H, we have that G H G to the minus 1 in H. We have motivated that this is a necessary condition for it being possible to form a group by just looking at the addition of the cosets. Right. Okay. So now let's actually prove that this also gives us a group structure on the set of cosets. So it's the following proposition definition. So, so if we have a H in the group, your normal subgroup, so then quotient set of H of cosets with the addition AH, no, maybe not H, operation AH and PH AH is a group. And it's called the factor group. Quotient group. Of G by H. So the main point here obviously is that this multiplication has to be well defined. So the definition, an element of a equivalence class is called a representative. So we have defined the addition, the multiplication of the cosets in terms of the representative. So in order to well define it independent of the representative. So product. So, well, so we just write it down. It's actually also elementary, but sometimes I put something experimental. So A prime, B prime, and in G with the AH, A prime H, AH, prime. So that's same. That and write A prime equal to A H1, B prime equal to H1, H2 with H1 and H2. And H. So, well, and then we have A prime, B prime. This is equal to A H1, B H2. Okay, and now we multiply in a nice way by 1. So this is the same as A, B, B to the minus 1, H1, B, H2. And we can practice like this. So then H1 is an element in H, so B to the minus 1, H1, H is an element in H. So this means this is an element in H. So this is an H, this is an H. Like this, and so it means that and so that's A prime, A prime, B prime, H is equal to A. And so it's very cool. So the rest is trivial. So we want to show that this defines a group, but this follows directly from the definitions. So group actions follow directly. From those G. Just let me write down the activity. So there was AH and CH, CH. Well, this is then AH and CH equal to AH. And this, and then one can follow back. Yeah, this is the ACH. And reverse the step. And obviously, the neutral element is 1H, which is H, and the inverse AH is A minus 1H. So this is the definition of the quotient group. And so, for instance, we have the example that we can form Z. So we have KZ to the subgroup. Z is the subgroup of Z, and as Z is median, it's a normal subgroup, and so we get Z mod KZ with the include the addition. Is it good? Okay. So the next concept we want to introduce is that one that one always introduces when one studies anything which is that of homomorphism. So if you have some structure, which is usually a set with a structure, you're interested in the maps between such sets of structures which are compatible with the structure. Wow. Hi. Right now there's more. Hi. So that's. Have you met only testing before? is the teacher for the course. You haven't met, no?
No, I
Anyway. She was a diploma student 2 years ago.
haven't.
What?
Three.
Three. Okay. So, and now she's a student at the CISA. PhD student. Okay. So we were talking. So I had said that. So we're talking about homomorphism. So for a group, obviously the structure is given by the multiplications. So group homomorphism is a map between groups which is compatible with the product. So definition. Let's use the H2 groups. Homomorphism. I should write it out because that homomorphism. And C. H is a map to H. And with the product in the group, so with E of AB equals A is to B for all AB in G. Very simple. So, for instance, so for the addition, we map A from the and N to K times N. Okay, great. So, and maybe another one which is but also with P from D to K was the numbers from 0 to K minus 1 with the addition by taking the rest, which sends number N to R of N, that's N dividing K. You can easily check. This is also different. That's the way the product, the definition of the product in the K is done in such a way that it's good. Just some. So in theory, there's a little bit more data to a group. We also have a neutral element and we have an inverse element. And these should also be preserved, but this follows from this. So let F from G to H group homomorphism. And then follows F of 1 is equal to 1, because this is the one in G, this is the one in H, and for all A in G, we have F of A to the minus 1. That's, I think that's, if you wish, an exercise that is completely trivial. It takes half a line symbols to write it down. We also have, so also as usual, the composition of group homomorphism is group homomorphism. And we can, and okay, and in particular, so bijective group homomorphism. The from H for the isomorphism. In this case, G and H are called isomorphic. An isomorphism of the group to itself is called an automorphism. Okay, so these are just the standard words that one always has. So obviously, it's also clear that if P comes to H is an isomorphism, and then its inverse is also an isomorphism. It follows directly from the fact that the map itself is compatible with the product that also is the inverse. Okay. And this is one step in seeing that, I mean, the obvious fact that being isomorphic is an equivalence relation on groups. And so in some sense, if two groups are isomorphic, that means for all means and for all reasonable means and purposes, they are the same. They have the same property. Okay. Obviously, we also want to know when the homomorphism, we also have the image and the kernel. The image is obviously the image, and the kernel is the inverse image of the element. Homomorphism. Then the image of the just the H and of G. H with the kernel is C to the minus with the kernel of E to the minus element. And now there are two things. The first remark is that, like in linear algebra, the homomorphism of groups is injective if and only if the kernel consists only of neutral elements. And P homomorphism is injective even only if the kernel equal to the neutral element. So it's also trivial, but still I please catch it. So obviously, if the map is injective, then it follows that the kernel only consists of one. direction. The other direction is not much more difficult. So to assume kernel of P just 1. So we take two elements, that A and B, two elements in the source, which map to the same thing. So I can multiply by P of P to the minus 1 on the other side. So it follows that, say, P of P to the minus 1. P of A of P to the minus 1 A. So P to the minus 1 A lies in the kernel, and so with this one. P to the minus 1 A. Multiply by B. So A. This is, and therefore everything there. This is simple verification. Maybe I should do this as before. So we can therefore, like in linear algebra, use the kernel to check whether homomorphisms between groups are injected. Okay. So let's just look at some examples of homomorphism groups, which is slightly less obvious. So F from M to N is a bijective graph. Can use this to compare the symmetric group on M and on N. So say we look, make map from the commutations of M to the commutations of N. So maybe like this. And by sending the permutation of M to the following, we take a point of N, we take its inverse image of -1 for sigma with F. If we have here M and N, so here is our F. So what we do is, so we first go back here to F to the -1, then we apply sigma, and then we apply F. And so this gives us a permutation of N. So if we have an element here, M at N, in N, we send F to the -1 of N, which is M, apply sigma to it, and apply F. So we move the element around. And you can easily see that this is an item. Obviously, the inverse map is given by replacing F by F to the -1. Anyways, this is just an example, but so we see in particular we have that so if M is that M has n elements, then the symmetrical group in M is isomorphic. So the symmetrical on n length, which was a permutation of the set of numbers from 1 to n. Okay, so this was this thing. Now we want to see simple but very useful thing. But no, I mean, we had already a special case of the map from, So obviously, if we have a normal subgroup of a group, and we look at the factor group, we have the obvious map from the group to the factor group, which sends an element of the coset, and this obviously should be a group homomorphism. And that's actually precisely how we define it, how we define the group structure. So lemma. Groups and normal subgroups. So then, what one usually calls the economical projection. T from T mod n, which sends an element A to its coset. It's a group of that this was precisely. And maybe I should also say with kernel n. So this is basically just a definition. Obviously, P of A times B is the AB n, which is AN times BN, which is PA. So it's a group homomorphism. And the kernel is n, also clear. So A is in the kernel of B, if and only if AN is n, which is if and only if A is in n. Okay, so this is so want to use another word which we don't really use very much, but it's a standard word in the language. So one thing you can think, if you have a group and a normal subgroup, you can go to the quotient group, and so therefore replace your group by a simpler one. In some sense, you can hope to describe the group G in terms of the normal subgroup and the quotient group. And so inductively, you can simplify your problem. So this works as long as there is a non-trivial normal subgroup. So a group is called simple if it doesn't have a non-trivial subgroup. It's only subgroups. Well, every group has some normal subgroups, and one consisting of the local element and the whole of G. Okay, so you cannot simplify the group G by dividing by a normal subgroup. Okay, so you put, for instance, check, and so example, the number of elements in the group is a prime number, then it's simple. This is just because we know that the number of elements in any subgroup must be divisor of the number of elements in G, and so the only subgroup of G, the only subgroups of G are G and 1. Other examples, so to wish this exercise is not. Try to find a normal subgroup. Now, a much harder exercise would be to show that Sn is simple. No, that's not true. Namely, yeah. Okay. So one should check what the normal subgroup is. I mean, you could try to.
A2 is normal subgroup.
What?
Alternating group.
Yeah, that's true. But I haven't introduced the alternating subgroup, but as you know, then this is the case. It would be, in other words, in this case, the cyclic permutations, where you send 1 to 2, 2 to 3, 3 to 1, or similar. Okay. So finally, for this thing, I want to show the homomorphism theorem. So this is about, so yeah, this is something which one uses all the time. It's again, some very simple fact, but if you have a surjective homomorphism from one group to another, then you can always divide the source by the kernel and get a new homomorphism. And somehow this often serves and actually get an isomorphism. And so up to isomorphism, it means that every surjective homomorphism is just dividing by a normal subgroup. And this is very often used to, to simplify some problems. So let's say C and D to H is surjective group homomorphism. So they are fixed kernel is kernel A. Yeah, obviously I forgot something. Maybe I can first that. So this is the lemma. So if it's just we have introduced the image and the kernel, so it's the C from H is a group homomorphism. And first the image of P is a subgroup H, and more importantly, the kernel of P is a normal subgroup. Of P. Maybe the first one we can get proof. If both sides are easy, maybe one I leave as an exercise. I mean, it's really trivial verification. Let's do 2. So let and the first one has to see the subgroup. So let A and B, the element in the kernel of B. So that means P of A is equal to P of B is equal to 1. So it follows that P of AB to P of A, P of AB is equal to P of A times P of B is equal to 1 times 1 is equal to 1. So AB in the kernel. And in the same way, P of A to the minus 1 is 1 to the minus is also, so say P of A to the minus 1 is equal to A to the minus 1 also equal to 1. So A to the minus 1. So this says it's a subgroup, and then normal subgroup has to do with the fact that it's actually the kernel. So so that A in the kernel E and G, and then I now make P of G to the minus 1 AT, like this, and this is P of G, P of A, P of G to the minus 1, which is like this. This one is equal to 1, and so we have 1 times something times its inverse, so this is equal to 1, and so we see that the kernel is a normal subgroup. And so now, and in particular, we can get this homomorphism theorem where we now say that we can divide by the kernel subgroup, and that in some sense all homomorphisms can be, and then we get an isomorphism theorem. Homomorphism theorem. So to H, projective morphism. Okay. Then we have an isomorphism. Then there exists an isomorphism in D bar of G mod K to H, which satisfies that P is equal to D bar composed pi. The pi was this canonical projection. We have diagram G composed pi G. Okay. This was pi. This is pi bar. Diagram. Okay, so this is this. So it's not, it takes longer to state it than it takes. But as I said, it is quite simple, but one somehow wants to use it all the time because it's somehow practical to say with the surjective homomorphism, replace G divided by the kernel, and then replace H by G divided by the kernel, and then go on. So let's see. Now, in the way I stated with the previous question, it's already clear what the answer is. Namely, it said here what that is the T should be T bar by pi. So this tells us precisely how this map should be defined. So the condition P is equal to T bar composed pi says that for A in G, for any A in G, we should have that P of A is equal to bar or maybe I say it the other around, P bar of AK should be equal to P of A. So that's what it said. Pi is the matrix that's A to AK. And so obviously if this is the condition that we have, then so if we want to have this, then the way to define P bar is that we define this. Now, obviously, this definition must make sense. So it has to be well defined. We have to find the image of this set AK in terms of a representative A. So it has to be independent of the representative. And in fact, we can at one step define that it's both well defined and injected. Well defined. Okay. If and only if. So A to the minus 1P is an element in K. The kernel of P is equivalent for P of A to the minus 1B. So this was the kernel of P is equal to 1. This is equivalent multiplied by A. So P I don't know, that was it. So no, P of A. What we see here is first, it is well defined. We have A and P, which represent the same coset, if and only if the image under A is the same. So this direction shows that the map is well defined. The inverse direction shows that it's injected. And furthermore, by definition, and P bar is surjective. Because what have we done here? We have defined P bar of AK equal to P of A. So every element in the image of phi is in the image of P bar. And we have assumed that P was surjective. Okay, so this was this. Right. So if I take one of course a simple example, so if we haven't yet so many examples, so if k is an integer, then we look at the map R from Z. So that what it was ZK. So R was the rest under division. This is the projective homomorphism. It follows, and I forgot one. No, yeah, and the kernel is all the things where the rest is 0 when we divide by k. So with kernel theta. So thus we get an isomorphism Z modulo k Z is isomorphic to this thing which I call Z. Yeah, maybe I don't quite know. Well, okay. Just maybe. Yeah, maybe I can see it. So that was so that was as much as I want to say about homomorphism. Now we come to group operation. This is somehow a little bit on the origin of group theory, sometimes where it comes from. So when people think of groups, they usually think of them as groups of symmetry. So you have some object, and there are certain things you can do to it without changing. For instance, you could have a square. If you look at all the rotations and reflections of the square, they form a group. And so that means, in this case, for instance, if you take the vertices of the square, this means that the group will move the vertices of the square around when it does this operation. And so this would be an action of the group on the vertices. Or even if you look at the symmetric group on n letters, it's defined by how it moves around the numbers from 1 to n. So therefore, we want to define this. So let's use definition. The set. So one somehow use the elements of the group to move elements of X around. So it's a little bit like if you're able to multiply elements in the set X with elements in the group. And there must be some kind of compatibility. So if you multiply by the product of two elements, which should be the same as multiplying twice, first by one element, followed by the next. And so that's basically all the definition that we have. So an operation for action of G on X is a map. Again, I denote it by times from G times X to X. We send the Gx to what I denote times X, such that we have two properties. The first one is really we want that the neutral element of the group doesn't do anything. So 1 times x is equal to x, or x and x. And the second is, as I said, that the product of two elements, x by x being first by one and then the other. So a times b times x, where this is the product in G, is equal to a times b times x. It represents some kind of associativity, but you don't notice that we're not in group. So this is the multiplication in G, and this is the action. So this means that this action is compatible with the group structure. So as I said, the example that we have already is that this n x on set 1n and by I have an element sigma in the symmetric group, which is a projection from set 1n to itself. If x on an element n, then will be k by just applying the k as a map. And you can check immediately that this defines an action. So I want to give some more examples. So, which surprisingly actually we'll use in the future, although they look so trivial. In particular, we can have a group act on itself just by multiplication inside the group. Although this looks like the, the fact that if I here x is an element in G, then this is the condition that one is a neutral element. This is the condition that the group that it's the multiplication in the group is associative. So we can have the group act on itself by multiplication. So let G be a group. So then G defines an operation which I hope L from E to G in the GH and GH in the group, so called left multiplication. This is a very trivial way in action because, as I just said, basically is the fact that we are in the group, so that this is an action. But surprisingly, one can actually get something out of it. One can use this to understand something about the group. Another natural action that one has to do with what we did with the normal subgroups, which is the conjugation action. So the GB group we have the action from P to P, which stands the pair GH. So, and G H G to the minus 1 is an action of G on itself. Or the conjugation. Just to make clear, obviously, if G is equal to 1, then this is 1 H, 1 to the minus 1 is H. And if we take AB, H, AB to the minus 1, this is A, B, B H B to the minus 1, A to the minus 1. And this, no, I can write this A B H B to the minus 1, A to the minus 1. So we first contribute the P and then the A. So this is also. So yeah. So one of the things is that now we want to come to apply these things to prove Cayley's theorem. Cayley's theorem says that every finite group is isomorphic to a subgroup of a symmetric group. And this is done by using this group action. Actually, the group action we use is a F multiplication. But the first thing that one wants to observe is that if you have a group acting on a set, then the multiplication with any element in G always defines the bijection of X itself. G act on a set X. So, given this action, the multiplication by P and G, I mean, which I mean the action of P and G on X is the map MG on X to X, which stands X, and X and X to G times X, the action of P on X. So clearly, by definition, H and 1, the neutral element sends every element to itself. This is equal to the identity on X. Now, note that for any G and G, we can look at first, we can apply, say, first we can apply MG to X, and all X in X, we can apply MG to X, and then we can apply mg to the minus 1 to that. What is this? By definition, this is G to the minus 1 times G times X. So where this is always the action, and by this kind of associativity, we have that this is equal to G to the minus 1 times G, where this is now the product G applied to X, and this is equal to 1. So this is X. So in other words, we find that mg to the minus 1 composed with mg is equal to the identity on X. And the same, obviously, the other way around. And so we see. So thus, all G in G, we have the MG X to X is the bijection. Or in other words, we have the MG is an element in this symmetric on X. And now you could ask yourself, so we can associate our element G in the group, this element MG, which is an element in the symmetric group, to have a map from one group to another. So the next question is it a homomorphism? And the answer is yes. So lemma. Yes. G and on X. Then the map M G. So the permutation of X, which sends an element G in G. So this map MG, which sends X to G plus X, is a group form. This is basically, again, just by definition, you kind of found a fancy way. So we're formulating the same actions once more. Namely, we take that U and A to the element in G, and the X and element in X. And then we have the definition. What do we have? If we take M of the product and apply to X, this is H to X, H times X. This is G times H X. This is M. Composed with image of X. And you know that the multiplication in symmetric group is the composition of projection. And so this shows this is a group form. And now we want to use this to prove Cayley's theorem. Then we want to use such a map to embed G into some symmetric group. Cayley's So every, I just say, would also hold for integral groups, but it's not interesting, so only with finite groups. So every finite group with G is isomorphic. The subgroup of the symmetric group and I can say which one, namely the symmetric group in and as many letters as G has L. Okay. And so we want to use this thing. So basically, we call that SG is isomorphic to S of G. So therefore, we want to establish an action of, use an action of G on itself, such that this map here, this group homomorphism, is an injective group. So we have that G is isomorphic to a subgroup. This merged group on G. And for this, we want to apply the previous lemma to the left action, the left multiplication by G. Apply previous lemma to left multiplication action. L from T times T to G, CH times the product in the group. So the lemma said that, so by the lemma, we have the map L from G to SG, which sends element G for maybe I want to say that I write the representation, rewrite LG for the map from G times G to G, G to G, which sends H to G times H. So then by the lemma that's here, we have the L from G to S of G, which sends G to LG, is a group homomorphism. And we want to claim its injective. For sure. L is injective. So if L is injective, then obviously G is isomorphic, so EH. The subgroup, the image of this map is a subgroup of G, and so this afterwards isomorphic to this map. So to show it's injective, we want to show that its kernel only contains one. So let's say G in element in the kernel of L. What does it mean? Then the kernel of L are all the elements which map to the neutral element of the symmetric group. The neutral element of the symmetric group is the identity. So then ALG is equal to the identity on G. So that means that LG was multiplication on the left by G, so G times H equals to H for all H in G. So in particular, G times 1 is equal to 1. This to G. So this is follows G is equal to 1 and the kernel, and so G is in. H is in. Or L is in. So thus we see that every finite group is isomorphic to a subgroup of a symmetric group, which somehow makes, in some sense, the groups more concrete. So you know that all of them live in some symmetric group. They cannot be something completely arbitrary. On the other hand, one has to notice that this is a rather ineffective way, because if G has a certain number of elements, then this symmetric group has, if the number of elements in G is n, then this group here has n factorial elements. So we have established every finite group as a subgroup of a much bigger symmetric group. But that's just the way life is. And in fact, this has even practical applications. If you look at, for instance, computer algebra things, if you want to use a computer to help you understand groups or construct groups or whatever, the way this is implemented, there are two ways: either to make the group as a group of matrices, or you make the group as a subgroup of a symmetric group. These are the only kind of general things to do. Okay. Okay, so this was how much time? Faster than I thought. So let me then briefly give you this example of a group, which is which I mentioned here, the diagonal group. So the symmetries of the regular n-gon, where the group is basically defined by both x on some. And I mean, it's anyway an important example of group. So, example. So the diagonal group. So I first say informally, so Dn is a group of symmetries of the regular n-gon by rotation and reflection. So in this case, it's natural to view it as a subgroup of a symmetric group, because such a rotation or reflection will be determined by what it does to the vertices. So if we number them from 1 to n, it somehow operates on the numbers 1 to n. So view it as n as a subgroup. what is F2 is a subgroup of Sn. By its action on the vertex. So, so maybe I number them cyclically. From 1 to n. So going. Oh, it's going. So we have this regular n bond where, so this would be, say, so you can see this regular, and then we have here 1, 2, 3, and the codon and the last one is n. Is n has 6. So, and now there are 2 things one can do. So we can either rotate, so we have one element is here the rotation by pi over n, so sigma. And then we can take the tau, which is the reflection along say the line which goes is orthogonal to the edge between n and 1. To the line and 1. So what can we say? So to make it, to view this as a commutation, what does sigma do? It just sends every element to the next. So if you have here 1, 2, 3, 4, 1, n, it sends 1 to 2, 2 to 3, 3 to 4, and 1, and the n is sent back to 1. And we have also tau. And that will always exchange an element by n plus 1 minus the element. So this means we have here 1 goes to n, 2 goes to n minus 1, 3 goes to n minus 2, and so on. So what happens here? The last one depends on the parent of n, which then means either this goes to the vertex or it does. So, and now you can see by these two operations, by these two things, we can, by combining them, composing them, we can do any reflection and any rotation of the regular n bond. So thus the dihedral group En is a subgroup of Sn, which is generated by these two. Generated by sigma and tau. Now recall that this means that we call that the subgroup generated by some set S was the set of all 1 times non-negative integer, and for all I, we have that xi is an element in S, or xi to the minus 1. This was how one could characterize the subgroup generated by some set. And now let's look. So in this case, we have two elements. And so what can we say about it? So obviously, we have that the order of tau, this is a reflection. If you apply twice to the identity, so this is 2. And the order of sigma is rotation if we apply it n times at the identity. Okay. You can, so that means that when tau squared is equal to 1, sigma to the n is equal to 1. And there's one further thing, you can check. Work this out with this description or intuitively from this. That if I take tau, sigma, tau, which is after all the same as tau, sigma, tau to the minus 1, because tau squared is equal to 1, is equal to sigma to the minus 1. So somehow, you can see it here, if you first reflect, then you rotate, then you reflect back, then you will have rotated the other way around. And anyway, it also follows from this. And so this is enough to describe this behavior completely, and we can easily see from this. The n can be described as the set of all sigma I, tau to the j, where the I lies in 0 and n, and the j is between 0 and 1. So this n minus 1. So this. All these elements are distinct. That they're all distinct, and you can just see what they do. And that this is the case, you can easily see, because by this relation, if you have the tau, some powers of tau on both sides of sigma, you can bring them all on one side. And then this relation means that the power can be made to be at most 2, and the power of sigma here can be made to be at most 1, and here it can be made to the power of sigma can be made at most n minus 1. Because if I apply 10 times, I get 1. And so therefore we certainly get this, and that they're all distinct. And so in particular, En is 2n. So here we have also an example of another non-commutative group, but it's somewhat mildly non-commutative. So you just have this relation here. Tau, sigma, tau is equal to sigma to minus 1. Okay. Yeah. This was the example of behavior. Yeah, okay, so I can briefly, I don't want to start something really new, but maybe I can briefly just introduce the word of the action being transitive, simply transitive, because we will use that in the future. Operation G on a set X is called transitive. Well, if the elements of G can move any element of X to any other element of X. So if for all elements X, Y in X that exist in element G, such that G is equal to Y. So the elements can really go everywhere. So every element can go everywhere. And it's called simply transitive if you can send any element to another one, but only in a unique way. Only one element sends a given element to another. If for all X, Y, and X, they exist in unique, so we write it there. Exist in unique. G in G with G times X is equal to 1. So now notice that if so this is just remark, but this is always useful. So if that X is non-empty, and G extensively, simply transitive, on X, then we have the map so for any X and X, the map from G to X, which sends X to G times X, is a bijection. So in particular, we have that the number of elements in X is equal to the number of elements in G. If we have a simply transitive action, then the number of elements in the set which is X corresponds to the number of elements in the group. And in some sense, you could also think, and this is sometimes a useful viewpoint, but we're not going to use it in this lecture, you can think then of X basically as if X was a group where you have forgotten which one was the origin. Because you have somehow which one was the neutral element. Because if you choose any element, you can define this map here. You can define a group structure on X so that this map becomes an isomorphism. And that plays a role in some questions in number theory. But anyway, that doesn't interest us here. Okay, so maybe I will stop here. Next, I will start talking about orbits and stabilizer, and then we'll go on from there. Are there questions? Also from the no? Everything is clear? Okay, so then I will stop here. Okay, thank you. So, I don't know what I should do anything. Okay, thank you. And I will go. So maybe weekend I will try to think of some exercises. And have a nice weekend, all of you.